Well, thank you. It's a very cold Boulder day here, 2 degrees Fahrenheit or minus 17 degrees Celsius. So I think it's heading toward DC. So brace for that coming up later next week, I guess. I'd like to thank many people, not by name so much because it's a long list, but for all the operations people and science data processing teams at LASP and at Goddard, as well as the other instrument teams. It's been a wonderful mission, wonderful data sets, and I'd like to thank the Eevee science team. A lot of what I'll show today is from many of the members of the Eevee science team. I will apologize. You know, there's hundreds of papers, and of course I can't represent all of those in 20 minutes, but I'll try to represent some good examples. I'll talk first a little bit about the instrument status, and then most of it will be about the science highlights. I think most of you know Eevee stands for Eevee Variability Experiment, and it measures the solar extreme ultraviolet irradiance. It is several instruments. The multiple EUV grading spectrographs, or MEGs, is what provides the 1 angstrom resolution from 6 nanometers to 106 nanometers with MEGs A1, A2, and B. We also have photometers. These are broadband photometers to help with calibrations as well as monitoring at higher cadence. The MEGs' primary mission was at 10-second cadence, and the photometers on ESP and MEGS-P are at 0.25-second cadence, and the ESP is provided by the University of Southern California. The little orange box there shows the 3 primary instrument papers. And then up here is the website where you can get more information and also publication lists. These 2 plots on this figure shows kind of the timeline in the top and the spectral range in the bottom, showing the different channels and what spectral range they measure. There's also SDO AIA in the shorter wavelengths, kind of in the similar as the red, but several broadband channels from AIA as well for imaging. We do have the one X-ray image called SAM that measures small, low resolution solar X-ray images. In the timeline above, the MEGS-A has stopped in mid-2014 because we had a capacitor that had a short, and even though we keep trying to test and hopefully that short would clear someday, it doesn't look like it's going to clear. So we get images from MEGS-A, but they're not useful images. So we have, that's basically 6 to 37 nanometers, but we do have continuation of MEGS-B and ESP, and of course AA continuing full speed ahead as well. We did notice early on in the mission that MEGS-B above about 70 nanometers had more degradation at first light than expected. We think that's related to the harsh radiation environment. We spent more time in the geo transfer orbit getting to the geo orbit, and we think that that degraded in that period, 2-week period. So because of that, we try to limit the amount of observations on MEGS-B so we can support a long mission. For that, we have basically a 3-hour daily measurement to help give us the daily average irradiance, which is important for our Earth atmosphere type studies that we do with the Eevee data. But also the flares are a very important part of SDO. So we develop flight software so that when the ESP channel, that's basically the 0.1 to 7 nanometer channel, detects a signal that's equivalent to a X-ray M1 flare, we start a 3-hour observation with MEGS-B. And the example shown here on the right bottom plot is showing that it got triggered for the M2 flare, and then it got re-triggered again for the M3 flare. So for every time the flare level gets basically above an M1, it triggers a 3-hour campaign. So that's been a very successful addition for the flight software. And the little tables, a busy table, you don't need to read it, but basically the point is, and I'll talk about this more in a few minutes, the MEGS-B and ESP provides a lot of the same information about flare energetics as MEGS A, as well as, of course, there's the AIA type images and similar information. So 3 of the importance aspects or science that we do with Eve observations. This is full disk irradiance. So some of our science is of course more heliphysics and space weather related, but of course solar physics is important too. And one of the main thing I'll be talking about today is some of the solar physics we've learned for flares. And the example of that shown here, and I'll show more examples, but the the number 1 left plot shows an example of a flare spectrum. What's important to use Eve data, because it is full disk irradiance for flare spectra, is you need to subtract off the pre-flare spectrum. And this shows an example where after you subtract off the pre-flare spectrum, you see that most of the energy of the flare is coming out at the helium-2 304 angstrom line. And that's pretty much true for most flares. The second point is Earth's atmosphere, not solar atmosphere, but Earth's atmosphere physics is a very important part of the energetics and dynamics in Earth's atmosphere. The ionosphere and thermosphere is related to solar EUV input and the variations of that. An example of that there in the middle is from Jan Soka, showing modeling of the ionosphere and how it looks different with using Eve data to understand the variability in the Earth's atmosphere. And the third aspect is space weather, and I'm really talking about space weather operations. Of course, the other 2 topics are related to space weather science and research, but the third bullet's really about operations and how NOAA and the Air Force uses Eve data and other SDO data for space weather operations. An example there on the bottom right is Rachel Hawk's analysis of ESP data to show how that relates to GOES XRS intensity. And then that model, which has 2 components, a hot component, basically flaring, or cool component, non-flaring, basically, is used to then predict the XRS X-ray intensity, and is used operational by NOAA when the GOES XRS instrument's not available. That is, their eclipses about twice a year. So that's an operational use of Eve data. So I'm going to kind of go into each of these a little bit more now. But first, let you see the list of science team members. Relatively small team. The prime mission, of course, we had more people, and then after the 5-year prime mission, we got a 30% cut, as typical for heliphysics missions. And then in extended mission, it's primarily the core instrument teams. The color coding there is sort of their primary role on the program, although of course everybody has multiple hats and play multiple roles. But you can see there's a fair amount of instrument scientists. We have 5 instruments on board, solar physics, Earth atmospheric physics, and space weather components as well. And then on the right is a list of graduate students that have used Eve data. These are students that we help advise or support their studies. There's a longer list, of course, that's used Eve data and other SDO data. So this is definitely a short list. So I apologize again, this is not listing everybody that's worked on Eve data. This is mostly the core group that's been funded by Eve. And thank you for your input to help make this presentation. The list of publications is shown there in the orange box. And again, there's hundreds of papers there that have, and of course, there's thousands of papers, as Dean has pointed out. So I'll give you a couple examples of solar physics that have been done with Eve data, and some of the kind of what I would call surprises or discoveries from Eve. The first one is related to what I call the Eevee late phase, where you see a second peak after the first main peak. So most emissions peak here along with the X-rays, and then on a few flares we see a second peak that's broader and later, and there's usually not an X-ray component for this peak, so it's not really detected in the X-rays, and I'll talk about this a little bit more later. A second component is corona dimming. Now that was known before SDO launch in EUV images, but we didn't really expect to see it in full disk irradiance, but we did. And James Mason has done a great job analyzing those data, or some of the data. There's still a lot more to analyze, but he did a PhD dissertation on this, and I'll talk about some of that as well. And Dean mentioned it earlier as well. But we do see dimmings in the cooler iron lines at the 1 to 5% level. And then the third aspect is Doppler shifts that we see in the emission lines. And we did not plan for Eve to measure Doppler shifts. So we were really surprised when Hugh Hunson contacted us soon after launch and said, hey, I see Doppler shifts. And he published a paper, and then Phil Chamberlain went and analyzed the instrument better and has a really good paper about how to use the Doppler shift information as accurately as possible with this. This is mostly with MEGS A instrument. So we only, of course, have the Doppler shifts for the first 4.5 years with MEGS A, but I'll talk a little bit about that as well today. So I think most of you are familiar with the flare phases. The impulsive phase and gradual phase, of course, is well known. Before SDO, the Newport effect is one example of that. The new things that we've added for irradiance measurements is corona dimming in the EUV late phase, and I'll talk a little bit about each of these. As known before SDO, the impulsive phase is mostly seen with the upper chromospheric emissions and transition region emissions. What Eve provides is a clear view of all these wavelengths at once. Because we're getting 10-second cadence data, we get the full spectrum in the EUV at this 10-second cadence. So we've been able to clarify better that most of the energy in the impulsive phase is from this helium-2 304 emission. And about a third of the flares, there's about 8,000 flares doing the SDO mission, and about a third of those flares have the impulsive phase. The second component, of course, or second phase, is the gradual phase. And this is, of course, best known through the XRS X-ray measurements from GOES, basically to classify the different flare levels, the C class, M class, X class flares. So basically, by definition, we look at that first to identify when a flare was. So by definition, all the flares we looked at, 100% of them have the gradual phase. And of course, in the EUV spectrum, they show up in the hot corona lines, primarily in the 9 to 14 nanometer region. And then the new stuff, corona dimming is one of them. And it was seen early on and been seen in thousands of flares. And about a third of the flares have corona dimming. This is often associated with a corona mass ejection, basically mass loss. And it shows up strongest in the helium, or not helium, sorry, iron 9 17.1 nanometer line. You see it in the other iron lines as well. And of course, each flare is a little bit unique, but there's some similarities from flare to flare and CME to CME. But what's really interesting is this has been kind of validated at the irradiance level from Eve with the AIA dimming. You can see in the left figure, these colored circles are where regions actually dimmed from this flare on August 7th, 2010. And it's a very complex interactions and global type effects. And when you add up all those dimming regions, this is a paper from James Mason in 2014, the red line here traces out the AIA dimming on the full sun of the disk of the sun. And then for Eve, it's the black measurement at 17.1 nanometers corrected for a impulsive phase component using the iron 15 284 angstrom line, the green line, and the result of that is the blue dimming. And that agrees reasonably well with the AA amount of dimming. And what's the second paper that James did, which is also a very important result looking at many flares and corona dimming effects, is the 2016 paper showing results here in the right with the dimming amount of slope being correlated with CME speed, that is this blue slope here, And then the amount of dimming, the depth of the dimming being correlated with the CME mass. And as Dean's already mentioned, and James has posted in the chat, there's a new mission being developed at LASP called Escape that will be using this lessons learned from SDO to look at stars. And of course, this is very important for exoplanet studies and life on other planets, other systems, by looking at stellar CMEs through this technique. So very exciting. It's in its phase A. There is a down select. Get selected here this year and start building hardware next year. And then the final aspect of the solar flares I want to talk about before moving on is about the second peak that we see in some flares that I call the Eevee late phase. There's been lots of papers about this. Some people call it also the hybrid flare. And we see this primarily in warm corona emissions like iron 15, iron 16. And you can see here the peaks mostly in those emission lines. The second peak is often like 5 minutes to 60 minutes after the first peak. The first peak, of course, being associated with a fairly large X-ray peak. And the second peak, there's usually no peaks in the X-rays. So Rachel Hawk did this study for part of her dissertation several years ago, and also looked at all the different flares and flare categories. But for this one, it took us a while to figure this out, thanks to a lot of digging and research that Rachel did to understand that basically for these Eevee late phase flares, there's a quadrupole magnetic configuration. The left image is not magnetic fields, but that's a shifting of image to show you flows. But basically you have a quadrupole magnetic fields where you have small, shorter loops. That's initiation of the flare, and then the outer magnetic field loops, which are longer, that both sets of loops get disturbed. The shorter loops cool faster, which is the first peak. The outer loops, which are longer, cool slower, which is the second peak. And it's a consequence of both sets of loops getting disturbed and reforming and cooling. That is the reason you see two peaks. Now, of course, there's multi-thermal and multi-loop effects going on. So there's constant heating as well. It's not quite just simple it's cooling loops only, but that's a part of why they show up at different times is due to loop lengths. Another example of that is a paper by Liu showing that the second peak for this November 5th flare in 2010 has 3 times more energy than the first peak. So this, of course, has important implications for what happens in Earth's atmosphere. And I also looked at how often does this happen? How often do we get EUV late phase flares? And I noticed with the comparison with SDO Eve data with XRS GOES data that there's 2 slopes in the X-ray data. On the figure on the left, there's a steep slope, which corresponds to the first peak in the EUV, and then there's a slower slope, which corresponds to the second peak in the EUV, and that's again related to the cooling rates being different for the short loops versus the longer loops. So I used that aspect, and I did an algorithm to find all the flares over the last 40 years. And that's kind of represented on the right plots. There's a lot of data here, but in the top right, just focus on the black. That's the number of EUV late phase flares detected. And you can see it follows a solar cycle. And this is detected using the 2 slope. If the X-ray flare has 2 slopes, then it says it was an EUV late phase. And then the percentage of that per year, again, there's a lot of information here, but if you just look at the black, you'll see that the black data has a peak before solar minimum and another peak after solar minimum. So this is the percentage of flares that have the EV late phase. So doing solar maximum, it's only like 5% of the time, but doing solar minimum, it's more like 10 to 20% with the peaks before and after solar minimum. I guess one concept for this is that at solar minimum, there's of course not many magnetic active regions. near solar minimum, you can have more complex magnetic active regions, but then as you get to solar maximum, the magnetic features are so complex and interactive that these EUV late phases configuration, this quadrupole configuration, doesn't show up too often, I guess. And of course, a lot of flare physics is understanding the plasma of the corona, and several papers have come out about that. A couple examples I'll show you. One is from Harry Warren in 2012, looking at deriving the D&M. D&M stands for differential emission measure, looking at that temperature and density profile over temperature on the right for a flare, showing that it's a very complex and broad feature, whereas a lot of what we used before SDO was just to use the GOES XRS data to give you an isothermal temperature, which is the vertical bars, blue bars in this figure, showing you the distribution of D&M it's much more complicated. And another aspect of that Harry has also looked at in his 2014 paper is the abundance of the first ionization potential, like iron and silicon and magnesium, looking at those changes during a flare. Typically that FIP or abundance bias is like a factor of 2 to 4 for non-flaring parts of the corona, but doing a flare, he was able to analyze 21 flares for this paper and find that the abundance factor relative to the photosphere abundance is about 1, showing that there is heating and cooling with the energetics that expected with the standard flare model. And then the figures on the right are similar type view of the differential emission measure, but for non-flaring times. So this is analysis I had done this year to model the daily variability of the sun. And there's 2 components. You need a quiet sun component and an active region component. And the quiet sun component, which is a black line, it's kind of hard to see under all this, agrees very well with the quiet sun ice measurement that's in the Chianti database. The active region component rolls off sooner than the standard Chianti active region, but we have now 2 new reference D&Ms from Eevee. I'm running out of time here, so I have 3 more slides. One on the Doppler shift, showing the stuff that Hugh Hunson discovered for us, and some more analysis that Phil Chamberlain has done later, but showing Hugh's early results, showing that the helium-304 in the middle image showing downflow as expected and seen in other measurements before SDO, and then also the Doppler blue shifts for hot corona showing the outflows. So very good example of that. The other aspects we're saving basically for a future science meeting. I believe on April 8th, we'll have more discussions and presentations about Earth's atmospheric effects, such as shown here for space weather climate, ionosphere and thermosphere effects in Earth, as well as on MAVEN. This has been an important part of the NASA MAVEN Mars mission that also studies the ionosphere effects with using Eevee data as well. And then the final slide I really have is on the space weather operations. Again, we're saving most of this for a future meeting. I think it's planned for April 22nd. We'll talk about some of the space weather operation aspects of using ESP data for XRS proxy, modeling for those operational model, using Eevee data that Ed Thiemann and Frank Parve has developed. And also there's some physical parameterizations that Ed Thiemann has developed using this equation that can predict the cooling effects from these emissions from Eevee. So I'll close there with kind of a highlight there of some web links and just an example plot of the FISM model that Phil Chamberlain has that's been updated last year, going back to 1947, help with space weather climate type studies and showing kind of where we are in the solar cycle. We're finally starting to ramp up for solar cycle 25. So thank you for your attention.